Afternoon and welcome to this A-level maths topic deep dive into trigonometry. My name is Stuart Bullock-Saunders and I'm the product manager for GCE and Level 3 Mathematics here at Pearson. I wanted to give a brief overview of today's session before handing over to Jocelyn to take us through the event. Today we will look at the specification requirements along with some exam style questions along with some examples of candidate responses. We'll also identify some useful resources to support you in the classroom along with all of the relevant links. Please do feel free to use the chat to either ask questions or provide your feedback during the session. I will be on hand to answer any queries that do come through there, and I'm sure Justine as well will be happy to respond where she can. I will now hand over to Justine to take us through this topic deep dive into trigonometry.
Thanks, Stuart, and hello, everybody. Welcome. My name is Jocelyn. I'm here as your subject specialist for Maths A-level, and I also work for Physics and Maths tutor, and I have quite a lot of experience teaching Maths A-level. So let me first show you the agenda. As you can see here, we'll mention very briefly the transition from GCSE, and I'm going to be highlighting the A-level spec for each part that we go through. So specifically, we're going to look at identities, graphs, and calculus. These were three things that came up in feedback to the previous deep dive in trigonometry that we did. There are a lot of slides here, so my intention isn't to spend long on all of them. There are some that I know that I'd like to spend longer on, and others that we'll just glance through. But you've got access to the slides, so perhaps after the session you go back in more detail, or you can take out certain sections and look at them with your department, or even with your students. Some of them are student friendly. It would be useful if you have your calculator, if in case you want to try any of the questions. Like I said, I know which ones I'd like to spend a little bit longer on, and so with that, a paper and pen or something to write with. So very briefly, the transition from GCSE, we've got AS content in bold, and then you can see where we've underlined the foundation and higher tier GCSE. We're not going to be spending much time on this necessarily, just because of the three areas that I said we're going to look at. But obviously, using and understanding sine and cosine and tan will come up. Also, I should mention, as Stuart already did, we've got the chat. So please feel free to type anything in the chat whilst I'm talking, any questions, comments, and there'll be some times where it would be really great if you've got any ideas or techniques, if you can share those. Something else from the specification that links to the GCSE, again, we've got bold is AS, and then we've got foundation and higher tier underlined. And so you'll notice the thing that's not underlined is radian measure. So radian measure will be something that's new to your students, and actually it doesn't come up until year 2 or A level. And so there's a link to some transition support material. Okay, so it's quite useful for us to just have an idea of which formulae the students will have, so we know what they need to know off by heart and what they don't. So something to note is that the double angle identities, which I'll talk about more later, are not on here. So they need to be able to derive them or learn them by heart, bearing in mind that occasionally you can get a part A of a question which does ask you to derive them. Some of these come up more often than others, but it is worthwhile making sure that your students have seen all of them and are aware that they exist. And so in particular today, I will be looking at the differentiation and integration ones when we get to the calculus section. So you might want to either have this open separately or take a screen grab of it. candidates are expected to know. So we've got what isn't on the formula sheet essentially, and that includes your identities and that includes the reciprocal identities. And then, as I was saying, we've got the double angles as well. Notice there that on here we've got one cos double angle, but you can actually, there are three cos double angles. By double angle, I mean where it says cos 2a is identical to. So there are two others that are worthwhile knowing where you eliminate either the cos squared or the sine squared. They're a little bit more useful, I would say. Okay, so here's our first section, identities. Looking at the specification, we're going to start with AS or year one, so you can see in bold what they need to know. And I would say identities is a really good example of where the year two builds on the year one. So a strong foundation in this is really, really crucial. Um, Find the values of theta between 0 and 360 for which. And so something that you could talk to your students about is how do they identify which identity to use? So they've got their identity sine squared plus cos squared equals 1. They've also got sine over cos equals tan as a year one identity. So knowing which one to use, or, if they should be using one. And as I said, if you've got any hints or ideas, feel free to pop them in the chat. I would say looking for the one that is squared, so in this case, the cos squared, would be a nicer one to replace because their identity itself has a squared in it. Sine squared plus cos squared equals 1. Likewise, noticing the angles on either side. We've got a theta on the left-hand side and a theta on the right-hand side. So that kind of rules out the double angle identities because we want to keep the angle the same. We don't need to halve it or double it. Give your answers to 2DP so you can see here rearranging the identity, substituting it in to get a three-term quadratic in sine, and then solving from there. So a couple of things to point out. Coming up, deciding with your students how you're going to solve sine, cos, and tan, particularly how you're going to get additional solutions. So for example, I know some people like to use cast. Other people would get their students to draw the graph every time. So it's really up to you. Maybe try a couple of things and see what works best. Um, and also, it does say in italics there, be aware that this can be done entirely on their calculator, which is not acceptable. So it will say that in the mark scheme for the examiners. The only stage where they could use their calculator, oh sorry, the first stage they should be using it is to solve the quadratic. They shouldn't be using it from the get-go. So even though they could technically solve it just from the question, they should wait and not use it until solving the quadratic. But I would recommend that they solve the quadratic using their calculator because it has got that function. And then you can see how the marks are distributed there. We've got 3 method marks, 1 answer mark. Another type of question is a little bit different. So rather than solving here, we're proving an identity. So again, how can you get your students to think about this? So looking at the angles, they're the same on both sides. I'm noticing that there's a tan on the left and there isn't a tan on the right. My personal preference is to work with the left-hand side. You can get marks from going right to left. I like to go from left to right. And so that tan needs to go. Substituting tan with sine over cos. And then another thing that they've noted that has been actioned here in the first mark is combining the terms. So looking, we've got 2 terms on the left and we only want 1 term. So getting those over a common denominator. I'll just give you a moment, just a few seconds to think about the next step. So we're here with 1 plus sine theta all divided by cos theta. How would you proceed? Thank you. We've got a suggestion in the chat. Interesting question. Can we also work through both left and right and show it is equal? I mean, so one thing that I suggest to my students is if you want to work with the right, then start lower down the page and then work up. And then you can start with the left higher up the page and then get them to meet in the middle, if that makes sense. But I would be really cautious that your students are definitely showing the logical process to get from left to right if you're allowing them to do bits of both. Rationalize, yep. Okay, lovely. Thank you so much, everyone. Um, so I thought this was quite tricky because I don't think it's obvious. So one thing they can do is look at the right hand side and say, okay, we actually want a one minus sign on the denominator, and we're really quite far away from that. So let's introduce it. So as many of you have said, let's times the top and bottom by one minus sign. And then you'll see it does kind of sort itself out. But that step, the second mark, achieving that, is quite tough. And for all of these, we will have the examiner's report. So you can go and check what the key findings for each question were, or the key comments, I suppose. There are a number of completely blank responses to this question. Do note it's question 13, so it's late on. Most of the attempts started with the left-hand side. Many scored no marks at all, but quite a few combined terms of the common denominator, as we discussed. However, very few progressed from this, with many using identities such as, and then we've got some identities that aren't actually identities there. So if this was a tricky question. Now moving into year two or A level, again, we've got the specification. So noticing the bits that aren't in bold are our reciprocal functions, reciprocal identities, and we've got radians as well. Here we have the double angle formulae, and then these can be applied to understand and use expressions for A cos theta plus B sine theta in the equivalent forms of R and R or R. So I call this the R method informally with my students, but you can give it a name. So here we've got an example. This is quite standard, I would say. So we've got part A, it's 3 marks, express. We've got two terms, one with a sine, one with a cos, and we want to express it in the form. So more often than not, the question will tell you to do this. If you've done this before, then you'll know that one way is expanding this using the addition formula. One thing I see quite often is students expanding without using the addition formula. So they will just think that sine x plus alpha expands to sine x plus sine alpha. So you really want to try and avoid that. So always reminding your students to look at the formula sheet, and I suppose reminding them that sine is a function. It's not like we're expanding with another x or a y. We are expanding with a sine. So we have to use the addition formula here. And then we compare coefficients. Once you've compared coefficients, you square, add, and square root both sides to find r. And then you divide. Again, another sticky point is remembering to divide the right way around. Common mistake is students will divide the wrong way around. We want to divide the sine over the cos so that we can use our tan identity. Please always encourage your students to write out the final answer. It's not always worth a mark, but here it does say express in the form. So here I would definitely want them to write it out. I thought I'd pop on here a quick way. Does anyone teach this to their students using, I'm going to say it's a shortcut or the quick way? Yes. It's not for everyone, I'll be honest. It's more of a time saver. I would always introduce this using the comparing coefficients method, always. But then if I've got students that are super quick, super happy with this, I might tell them that actually all you ever need to do is square, add, and square root the coefficients to find R. That might seem quite obvious. So rather than expanding, just look at the coefficients. And then this is the bit that not everyone likes. If we're writing it in the form R sine, which is what we're doing here, then they need to divide the cos coefficient by the sine coefficient and do tan inverse of that. If they were doing this in the form R cos, then they would do the sine coefficient divided by the cos coefficient. So you can, yes, so some people do the quick way, but then still return to co comparing coefficients for the second part for finding alpha. It's not for everyone, I admit that, but for your students that want to speed up time, maybe your A-star students, I recommend it. This question is a little bit smaller, but hopefully you can see that. A common part B or a common follow-up to our method is modelling. There's actually a great modelling resource that I will point you in the direction of later that actually has this question there. So modelling, we need to use our previous answer. It's 1 mark here, so often there'll be a follow-through mark if they've got the previous part wrong, as long as they apply the correct rules to find, in this case, the maximum. So we've substituted in our previous answer, but then we've noticed there's a +5 that's new, so let's put that on, and then we can find the maximum temperature. So different ways of finding maximums and minimums. So in this case, it was a maximum, so we took the value of the sine graph to be 1. That's how I would describe this. So I took the value of the sine graph to be 1. 1 times root 5 is 5, plus 5 is root 5 plus 5. If anyone's got any alternative ways that they do that, please let me know. Another tip is with your students, if they're unsure, yes, I will also be looking at some graphs, some GeoGebra and some graphs for this type of thing, and I'll try and mention how it links back. So in terms of transformations, because I haven't got a GeoGebra set up for this right now, in terms of transformations, so you've got the things inside the bracket are only affecting the x-axis, so that's not going to affect the max and min. That's going to be shifts and squashes in the x or in the horizontal. So the things I'm looking at are the root 5. So that's going to affect the y-axis. So the original maximum was a 1, but we're going to get times by root 5. That's a stretch. And now, following the order of operations, the graph then gets shifted up by 5. Hence why the new maximum is 5 plus root 5. I hope that makes sense. Little tip is, why don't you get your students to also sub in a 0 for the sine graph and a -1 and see which one produces the maximum. It is going to be the 1 in this case, but sometimes it's the 0 and occasionally it's the -1. So I'll say that one more time. So sometimes the -1 can produce the maximum when you come to sub it in. It's worth looking through past paper questions to find different examples of these to show your students. Briefly, I wanted to mention on the examiner's report, if you look at part B, occasionally candidates obtained an answer of 8 from 5 plus 1 plus 2, which they obtained from taking the maximum values of sine and cos. So that is problematic. So there they haven't used the R method, and what they have not understood is that the graph is not just going to be the result of the maximums added together. They need to understand that the graph, if I just go back, the graph sine x plus 2 cos x, um, they need to understand what that looks like. And so you can show them that on GeoGebra. Here in student responses, we've got a common mistake with the dividing the sine and cos the wrong way around, or actually they've divided sine and cos the right way around, but they've divided the right hand side the wrong way around. So really watching out for that. This question I thought was interesting. So I'll just give you a moment to look at it and then think about how you would approach doing it. We've got one response, addition angle formula. Apply R sine. Nice. Any other ways from anybody else how you might do this question? Yeah. I think if I just in my head think through a few steps, if I was trying to introduce a tan, I think you would be able to solve it eventually that way. I think the problem we would have is if we just divided by cos now to get the tan, um, cancel the cos, we would also have a sec on the right hand side. So you wouldn't just have a tan, you'd have a tan and a sec. And then you would have to return to the way that some other people have suggested, which is squaring. So this was a leading question. I was hoping that you would give a few different answers, which you have done. So a good way of doing this is the R method, even though it hasn't explicitly told you to. So here I'm showing you how you can do this with R sine. You could also do this with R cos. So you can choose. It can always be done with either, unless they're telling you, no, we want this way. But it works both ways. The issue with squaring both sides that can occur is extra solutions. So I'll just read out a short bit from here. A second strategy was to square both sides and apply the identity sine squared plus cos squared equals 1. In both of these strategies, extra incorrect solutions were generated as a result of squaring both sides. So if you are going to let your students square both sides, there's no problem with that, but they have to check their answers at the end. So they need to plug them back in and check them because some of them will not be valid just through the nature of squaring and square rooting. So the R method would be the safer route to do. Um, Here they're calling that the third strategy. And you can see that you're allowed to write it in terms of sine or cos. A few students applied other correct strategies, which led to solving quadratics in either tan or cot. We mentioned that one as well. So here you can see this is an example of the squaring. They've actually done it they've just rearranged the identity and then subbed it in, but with the square root sign. But it's the same idea. The problem with this one is they stopped after finding one solution. So they didn't do too badly, but they needed to find more solutions for the cos graph. And here they've gone for R sine, which is a really good idea. The problem with this solution is the student has left their work in radians, whereas it needed to be in degrees. So they will not score full marks for that. Okay, left-hand side, right-hand side, combining common denominator, and then take a look at this one. Again, I chose this one because I thought it's might stand out. It might be quite tricky for students and for us sometimes. So if you have a look, we've got the 3 theta, and in the numerator, we've got cos 3 theta, cos theta, plus sine 3 theta, sine theta. And what you needed to recognize is that that's the addition formulae. And so you can write cos brackets 3 theta minus theta, or in other words, cos 2 theta. You can see where I got this question from. This is June 19, paper 2. And then from there, it wasn't too bad. And you can see you have to use another addition formulae on the sign. So getting your students to investigate what the angles are on either side. Are they doubles? Are they singles? Are they a mix? I always get my students to look at the angles before proceeding. Hence solve. So you really needed to have done part. Well, no, you need part A, but it was a show that question. So you've got the right hand side. So you really do need to use the right hand side and replace it where the left hand side was, set it equal to 4 and solve. Solving for 2 theta, when you've got your 2 theta solutions, you divide them by 2 for theta. And so part B was a 3 mark, so all 3 marks are available to students even if they were unsuccessful in part A. So this is a good example of that. This student was unsuccessful in part A, but then they've gone ahead and persevered and done part B anyway. Okay, so we are on to our second section, graphs. Jumping straight into year 2 or A level, as this is where most of the examples appear. There's a snippet from the specification. And here you can see we've got a modeling question. There appears to be a Ferris wheel. There appears to be a sine graph. And this is also a resource in the modeling questions resource, which I'm going to show you later. That can be found in the Emporium. I'm going to give you a minute or so to read this through to yourself. If you want to go ahead and try and find the complete equation, please feel free to go ahead. We're looking for the exact value of A, the exact value of B, and alpha to 3SF. And so remembering the things inside the bracket, that's going to be your horizontal transformations, and then anything outside will be your vertical transformation. So we're looking for a maximum height to be 50. Height is 1 meter above the ground when the wheel starts turning. And the wheel takes 720 seconds to complete 1 revolution. So maybe you had a time to think about at least one of those values. Here's the answers to part A, the mark scheme. These are independent marks, B marks. We've got A equals, they're allowing plus or minus 50, and B equals a quarter. And then for the second bullet point, when time equals 0, so when it starts spinning, we get our value of 1.15. So making sure your students are aware of what the cycle of a sine graph is, or period of a sine graph is. So the full graph, so it has a period of 360 or 2 pi, but here we've actually only got a little bit of it, don't we? So this just has a period of pi, usually, or 180. And knowing that cos has the same period, 360, and knowing that tan has a period of 180, and they should know the max and mins of all of those. I actually use knowledge of the graphs rather than cast. So if my students are solving sine x equals half, I would want them to know that they pick up their calculator, they get an answer, and then they do 180 minus using the property of the graph. Here we have mock set 2, paper 1, question 8. We've got a cos graph this time. And again, I just wanted to give you another example of why it's good that your students have seen the graphs before they go into the exam, so that they can do things like identify where P is, which is a minimum. And then we're going to solve where it equals 4 sine x. So you would do that algebraically. I think you'd expand the left-hand side using the addition formula. But actually, you could also show it to them using the graph. So where do they intersect? So drawing 4 sine x on there, and then glance down to part C. So thinking about the transformations of the graphs and how that would affect the number of roots to the, well, it's the same equation, but we've transformed the x-axis. I'll point out part C here for you. So deduces the number of roots is 40 with the correct explanation, e.g. states that there are 10 cycles of 360, and x moving to 2x will mean that there are 4 roots between 0 and 360, not 2. So yes, it did say, if you look at the domain in part C, it said x is between 0 and 3,600. That's why they've mentioned the 10 cycles there. Quite a neat question, I thought. Someone in the chat mentioned that their students really like the modeling types of questions and the R method. One thing I did is I just went on ChatGPT and I asked it to generate some examples of when trig modeling is appropriate. So this could be something you could do, a starter activity, and I quite liked it. It, without me asking it to, it came up with some answers that are actually relate to the large data set in statistics. So it's talking about daily temperature. We've lost your sound. Can you sound as okay? Okay, thank you. Um, so yes, as I was saying, we've got something that links to the large data set there. So looking across the pure and the stats, if you like. And we've also got the things that can't be modelled with trig. And then it gives the reasons as well. Obviously, I would always fact check everything that I typed in on ChatGPT before showing it to my students. We've mentioned GeoGebra briefly. How can we use it for the R method? So this is a really great resource. The link is in the PowerPoint, GeoGebra/u/Pearson Maths. And then this is already set up for you and it links directly to the R method. So you can change the value of R by sliding and you can change the value of alpha. It's really fab. And then you can also see on there, there's the original equation as well, where it's split into sine and cos, y equals 3 sine x plus 4 cos x. And for modeling max and mins, likewise, another good resource there to investigate. Okay, so I'm moving on to my last section. It's quite chunky. Here is the specification. We've got differentiation from first principles, which is a year one, introduced in year one, but then year two, we look at it with regards to trigonometry. And we're straight into year two examples for that reason. So parametric differentiation, find an expression for dy by dx. So they need to be able to do dx by d theta, and they need to be able to do dy by d theta. Common mistakes are forgetting to times by the derivative of the bracket. So when they're differentiating y, hence find the exact value of the gradient. And that almost, well, let's have a look at how that one pans out. I was going to say that almost turns into something, like a year one question, coordinate geometry, but I think it might be a little bit trickier than that. So here you can see in the mark scheme on the right, we've got dy by d theta. As I was saying, you need to not only drop the power to the front, decrease the power by 1, you also need to times by the derivative of the bracket. In this case, you don't need to prove the derivative, you just need to write it down so you can take it from the formula sheet. Highly recommend your students are familiar with what is on the formula sheet. Otherwise, they could spend ages trying to derive it, trying to derive the derivative of cosec using 1 over sine. But they don't need to. And then the other derivative was quite straightforward because we didn't have to do chain rule there. And then part B looks like it's some substitutions, making sure that they're working in exact. So not picking up their calculator too soon, in other words. I um I had a different way of reminding my students how to differentiate sine and cos, but then this came up in when I was with some teachers the other day. I don't know if anyone else thinks of it as a circular diagram. I was kind of thinking of this linearly, but you can differentiate if you go clockwise. So derivative of sine is cos, derivative of cos is minus sine, and so on. And then you can integrate anti-clockwise. Just something to help your students remember what the derivatives are when it comes to the negatives in particular. If you've got any other ways or tricks to help your students remember things, please feel free to pop them in the chat and share. Briefly, again, just pointing you in the direction of GeoGebra resources that relate directly to the things I'm talking about. So this is showing multiple graphs on one sketch of, in this case, you can show f of x and you can show the derivative, so f dash of x. Implicit differentiation. So this is again, I'm going through all the things that you'll need to touch on or go into detail on that apply to trigonometry and calculus. So you'll need to do implicit differentiation. X squared tan y equals 9. So knowing the derivative of tan. And how to differentiate implicitly. And you can see in the top right there, I've put a snippet of the formula sheet in. So once again, you can see what the students are allowed to pull in for themselves. So the derivative of tan sec squared is already there for them. And then we're using the identity tan squared plus 1 equals sec squared. I say to my students, they'll just know those identities off by heart if they're practicing enough, the reciprocal function identities. But if in doubt, rather than accidentally getting it wrong, why not just prove it on the side of the page at the start of the exam? Because proving the reciprocal identities does only take 30 seconds or so. Can you show the derivative of a raised to power kx? Let me keep going. I might have one of those. Hopefully I do, and we can look at them. Here, parametric integration. a really fab question. June 2022, quite near the end, if not the end of the paper, question 16. Take a moment. So part A is a show that question. So they'll need to differentiate x, so dx by dt. We've got a sine squared, so that we're going to be using chain rule there. And then there's not too much to do other than work with identities, because before showing you the mark scheme, I'm just noticing that we've got a 2t in the angle for y, but in the answer, oh, in the answer we've got a 4t. So that suggests to me we're going to be using the double angle identities from right to left, maybe, rather than left to right. We're going to be, um, rather than halving the angle, we are indeed going to be doubling it. And the thing I wanted to show you was part B. Hence, use integration to find the exact area of R. So before I click onto the mark scheme, can you just have a think about how you would integrate that? In particular, how would you integrate the third term, 48 sine squared t cos t? How would you integrate the third term, 48 sine squared t cos t? Reverse chain rule, reverse chain. And what would it give you? What would you get? Hmm. Wonderful. So we've got a few people have written reverse chain rule in the chat. That's great. I actually call this integration by inspection. So looking to see, have I got the derivative sat next to one of the terms. So in this case, I have, because the derivative of sine is cos. I call it recognition. Nice. So someone in the chat has said I call it recognition. Sometimes I'm a bit hesitant about reverse chain rule, because my concern is that students are then going to start dividing by trig functions. So my concern is that they try and my concern is that they would try and divide by a sine or a cos, and that's going to be really problematic. One of my students years ago called this the guess and bodge method. Yep, I like that. So I guess and check. Yes, I really like this. So when I'm first introducing this, I will do exactly that. I'll ask them to guess, and then we'll differentiate that and see if it comes back to the original, which I think is what some of you are saying you do as well. So guess what the integral is, differentiate it to check to see if you were indeed correct. And so, yes, thank you. In the chat, we did have the correct answer. So that's 16 sine cubed t. I'm just looking at part B there. And then part A, you can see it's quite complex, really, isn't it? So you can see we had the derivative of x and then substituted it all in for parametric equations. And then, yes, the third mark attempts to use cos 4t equals 1 minus 2 sine squared 2t. That's a double angle identity, but we've got a 4t as the angle on the left-hand side. Examiner's report. A significant proportion were unable to integrate the third term to get an expression in sine cubed t. And you can see they also use the words reverse chain rule. Integration by substitution, so another type that's related to trigonometry. There's quite a few slides for this. I'm not going to spend too long on them just because I'm conscious of the time. I want to be wrapping up in just over 5 minutes. But this is a resource that I will mention again later, which is the exemplars. So this is all taken from the exemplars. This is all available to you for lots and lots of different questions. So firstly, it just gives you the question, integration by substitution. I think the bit I wanted to show you the most was probably, well, I wanted to show you all of it, but particularly the integration, because we've got a sine squared. So particularly the integration, because we've got a sine squared. So I always say to my students, if you've got a trigonometric function squared, you need to be really, really careful about how you proceed. So this resource gives you student responses, so you could give these to your students in class and get them to look at them or comment on them or mark them, or you could do the same. Usually they give you 3 responses. I'm not going to go through all of these now. Then it will give you the mark scheme. So you can see here, the bit I was talking about, part B, we're trying to integrate sine squared. You need to take the double angle identity for cos 4 theta and rearrange it so that we're no longer integrating that squared trigonometric function. And you can also see the workings for part A as well. So this is a really, really meaty question. What I love about this is it then goes on to give you the marks for each of those responses and a little bit of detail for them. And here, and finally, the third response as well. So you'll be able to see there are some common mistakes here. There are some less common mistakes here. This student got 1 out of 4 for part A and then 4 out of 4 for part B. Wow. So there you go. There's an example of someone persevering in the second part of the question. I think that's really impressive. The exemplar will also give you some key findings or examiner summary. So part A, we had incorrect derivatives for dx by d theta. Some issues with limits. That does come up, doesn't it, with substitution. Part B now, candidates who recognize the requirement for using double angle formulae were generally successful. Main errors in this part were in sign errors in the double angle identity. Yeah, okay, so perhaps they mean from rearranging it to substitute it in to use. Key takeaways. And I really like this as well. So we get the performance data. So you can see the max score was 8. So it's out of 8. The mean score was 2.41. So quite a low scoring question. It was question 13. It was right towards the end. And you can also see the mean scored by candidates achieving grades. And so you could say that this is an A star indicator question because there's quite a big jump up from in number of marks that the A star candidates achieve compared to before then. Okay, I'm going to look through some resources with you. GeoGebra I've mentioned, and so if you go to this link, you can scroll down and see GeoGebra resources for loads of different topics. I also use it in mechanics as well, be quite helpful. The Maths Emporium, it's free. You just need to get your login approved. I highly recommend you get access to this if you haven't already. There are cabinets for things, so I'm just going to draw your attention to a few of them. I'm in the Maths Emporium A-level maths, and you've got teacher guidance in there. You can look at teacher guides, specimen and sample assessment materials, practice papers, past papers and mark schemes, shadow and reordered papers. So if you're trying to assess your students on whether they've improved over time on the same types of questions. Examiner reports and exemplars. That's what I've been talking about in my most recent example. GCSE to GCE transition resources. I mentioned that right at the very beginning. That's just inside that cabinet, what you can find. Teaching and learning materials. So in teaching and learning materials, you can click on pure maths modeling questions. So this is a bank of questions that are focused just on modeling. And that's where I got at least one of my questions today from. And there's BSG worksheets as well, arranged by difficulty. So good for differentiation. And, they are appealing to students as well, pushing themselves to see if they can move on from bronze to silver or answer any silver questions. Likewise with the gold. That's within the BSG cabinet. There are topic tests, and that's it from me. So thank you so much, everybody, and thank you for participating in the chat. It was really lovely to hear from you. I'm going to now hand back over to Stuart.
Thank you so much, Jocelyn, for taking us through that session today. So I'll just finish up with a few of the summary and some further support that is available to you. So just a quick summary of what we looked at today. So identifying the key resources from Pearson that support you in your teaching and delivery of trigonometry, as well as looking at some of the exam style questions and some of that candidate performance as well. So a couple of recent releases that we have made. So on the Pearson website, you may see there's the AS Mathematics Mock Set 5, and we've also released a full set of A-Level Further Maths Mock Set as well. So they are on the Pearson website, so you can click on the links on those slides. They're under silver padlock to try and keep them as secure as possible, but do check those out. We've also produced this A-Level Maths command word poster, so great resource to be using either at the front of class or to be put up in your classrooms. They're just some of the key command words that are used in those papers for A-Level Maths and A-Level Further Maths, just to kind of help your students know what to do and how to attack some of those questions. And then our next topic deep dive will be on the 11th of March, and that is on the probability distributions. So again, you can sign up through the PD Academy by clicking on the link. And Jocelyn as well is taking us through that one. You may have seen as well in the chat, we've had Vicky supporting us today. So Vicky is our subject advisor. She is a font of knowledge of all things maths. You can sign up for a meeting with Vicky to have a chat with her if you've got any queries, anything you're not sure about, to get some expert advice. You've also got links to the Facebook pages for the different groups. So it's a great network of teachers and a way of sharing resources, sharing ideas, and being up to date as well with everything that's happening. A few extra bits that are included in qualification fees. So the Exam Wizard, so a great way to build some past papers or build some papers and resources. Results Plus, I'll also put a link to the Results Plus Central Analysis tool. That's a great tool to delve into the subpart and question part of your Results Plus data. And also access to scripts, so you can view your candidate scripts. So if you haven't done, really recommend taking a little bit of time to explore those different resources, different facilities and services that are available to you. To find out more about upcoming PD events, all of them are housed on the Pearson Professional Development Academy, so you can filter by maths, and then either Key Stage 5 or there's Key Stage 4. You've got all the different subjects as well housed on there. So do take a little bit of time to become familiar and see what other PD events might be of interest to you. And with that, just want to say a huge thank you to Jocelyn for taking us through today's event, and a huge thank you to everyone here for sharing your afternoon with us. I hope you have a lovely rest of the day wherever you are. Thank you very much.